Dear students, in this module we shall study about Gattermann-Koch reaction, Vilsmeir-Hock reaction and Diazonium coupling. So, if we try to look at the learning outcomes, you shall be able to study these named reactions, that is Vilsmeir reaction, Gattermann-Koch reaction, and you shall be able to learn and comprehend the conditions under which these reactions occur and analyze the product formed in these reactions. And in case of diazonium coupling also, you shall see how the diazonium compounds are formed, what are diazonium salts, how is the coupling reaction carried out, and then uses of these diazo compounds which are very important in the dye industry. So, let us begin our study with the named reaction, that is Gattermann-Koch reaction. This reaction is actually used for formylation of activated benzenes, that is introduction of the CHO group. So, what happens in this reaction is, that is the reaction of an aromatic substrate with carbon monoxide and hydrogen chloride gas in the presence of a Lewis acid like AlCl3 as catalyst to form aromatic aldehyde, and then this is called as Gattermann-Koch reaction. One thing very interesting you can notice in the name of Koch, the CO, which is carbon monoxide, is there as in an inverted form. So, that is going to help you remember that what is the reagent used in the Gattermann-Koch reaction. So, this reaction is carried out either under pressure or in the presence of cuprous chloride. And as you can see in this general reaction shown here, it is CO plus HCl. In C2 they will be giving rise to formyl chloride. Formyl chloride otherwise is unstable, so it is prepared in C2 with the help of carbon monoxide and HCl. And later on this AlCl3 acts as a Lewis acid and it will generate the electrophile which is CHO plus, which will be attacking on this aromatic substrate and giving you this CHO introduced in the ortho or para position, because we will be taking here the activated benzenes as the substrate. Now, let us try to understand the mechanism of Gattermann-Koch reaction. The reaction proceeds via generation of electrophile by the combination of carbon monoxide and HCl in the presence of AlCl3. So, the electrophile HCO plus, where the positive charge is on the carbon, is generated, which then reacts with the aromatic substrate in an electrophilic aromatic substitution mechanism to give you the formylated aromatic compound. As you can see here, HCl combines with carbon monoxide and it gives you HCOCl, and in the presence of AlCl3, AlCl3 will take the Cl minus out and you have the formation of HCO plus, and this acts as the electrophile, attacks on this activated benzene, and followed by deprotonation, the product which is the formylated product is formed. Under high pressure condition, high yields are obtained in this reaction, and to overcome the limitation of high pressure requirements, because it is difficult to maintain high pressure conditions in normal labs, super acidic catalysts have been developed. For example, superacid generated from trifluoromethane sulfonic acid, hydrogen fluoride and boron trifluoride have been used. Now, after knowing the Gattermann-Koch reaction, let us look at the limitations of Gattermann-Koch reaction. The role of CuCl is not precisely clear, but it is known that CuCl combines with carbon monoxide and this adduct may aid in the reaction between HCl and carbon monoxide. So, Gattermann-Koch formylation method has many limitations, because there are many other methods available for the formylation of aromatic compounds that you are already aware, like the Riemann-Tiemann reaction and so on. After studying the Gattermann-Koch reaction, let us now move to Vilsmeir-Hock reaction. The reaction of electron rich aromatic compounds with N,N-dimethyl formamide, that is commonly abbreviated as DMF, and phosphorus oxychloride, that is POCl3, to yield an aromatic aldehyde is known as Vilsmeir-Koch reaction. Now, as you can see in this general reaction, you have this aromatic substrate, and when this is being reacted with NN-dimethyl formamide in the presence of POCl3, this is also leading to the formylation, that is introduction of the CHO group. If we look at the reagents which are used in Vilsmeir-Koch reaction, the Vilsmeir complex employed in the formylation reactions are usually derived from NN-dimethyl substituted amide and POCl3. The NN-di substituted amides which can be used are N-methyl formamide, NN-dimethyl formamide, N-formyl piperidine and N-formyl indoline. They all have been used even in addition to the DMF. Other amides such as NN-dimethyl acetamide, N-methyl acetamide, NN-dimethyl benzamide, etc. have been employed in the presence of POCl3, but these amides are prone to undergo self condensation, so they are not preferred. If you look at the various acid chlorides which have been used in the Vilsmeir reaction, in addition to POCl3, they are COCl2, SOCl2, ClOCl, CH3COCl, ArCOCl, ArSO2Cl, PCl5, Me2NSO2Cl and RO2CNHSO2Cl. If you look at the solvents which have been used, we have DMF, dimethyl acetamide, N-methyl pyrrolidone, etc., which are liquids, and an excess of the amide can be used as solvent. Other solvents like chloroform, methyl chloride, benzene, toluene, orthodichlorobenzene, dioxane and tetrahydrofuran have also been used. Now, coming to the details, and let us look at the structure of the Vilsmeir-Koch complex first. Phosphorus oxychloride reacts with tertiary amides to give adduct which exhibits salt like properties, and these adducts have been referred to as the Vilsmeir complexes. And as you can see here, starting with this NN-dimethyl amide as shown in this equation, when it is reacted with POCl3, first of all the POCl3 will be adding Cl to carbon and POCl2 to the oxygen, and it further dissociates and gives you this salt which is shown here as the Vilsmeir complex. Now, let us try to understand the mechanism of Vilsmeir-Koch reaction, that is how this particular reaction leads to the formylation of aromatic substrate. The formylating agent here is the chloromethylaminium salt, which is we have just now seen is called as the Vilsmeir complex, which acts as the electrophile in an electrophilic substitution reaction with the aromatic substrate. The initial product of the electrophilic aromatic substitution step is unstable and easily hydrolyzes to yield the aromatic aldehyde as the final reaction product. With mono-substituted aromatic substrates, the para-substituted aldehyde is formed preferentially, and you can see in this equation here the mechanism is shown that you have this NN-dimethyl formamide which attacks through the carbonyl carbon, which is being made electron rich from the lone pair over the nitrogen, and then as it acts on the phosphorus, one of the good leaving groups, the Cl minus, goes out, and there is the addition of POCl2 to this. Furthermore, in the next step, this Cl minus will be attacking on the carbon, and there is a loss of PO2Cl2 minus, and you have the formation of this, and this is this and what you can see here is that as a result of this combination, there is the formation of this electrophile which is then readily attacked by the electron rich benzene, and as a result we have this substituted product which undergoes deprotonation, and as a result we have this intermediate which undergoes deprotonation to give you this resulting molecule which further undergoes hydrolysis and gives you the CHO introduced in the ring. Vilsmeir-Hock reaction is applicable only to electron rich aromatic compounds such as amines and phenols. That is, it has to be activated benzene sufficiently with the electron donating group like NH2 or OH. Benzene and naphthalenes are unreactive, but anthracene gives 1 aldehyde in almost 85% yield. NN-dimethyl aniline gives 4 dimethyl aminobenzaldehyde in almost 80% yield. The method is particularly effective for compounds such as pyrroles which are not formulated by other procedures. So, shown here are the various examples, that is, if you start with this pyrrolidine and introduce the CHO, you have almost 85%. Then the next molecule also you can see here, there is a 97% yield. In case of anthracene, again the product is being shown, and when you have this NN-dimethyl type of substituent, then also you can see the formulation has been done. Now, after studying these two named reactions, that is the Gattermann-Koch reaction and Vilsmeir-Hock reaction, both of them are used for formylation. Let us now move to slightly different topic, which is diazonium coupling. And when we talk about diazo compounds, let us try to know what are diazo compounds. Diazo compounds are the compounds which contain N double bond group as shown here, and their general structure is Rn double bond Nr dash, and here R and R dash are preferably the arene groups, that is the aromatic like phenyl groups, and the azo group is the stabilized by becoming part of the extended delocalized system along with these aromatic rings. They are prepared by coupling reaction between a diazonium salt and a coupling reagent. Let us know more about them in detail. If you look at diazonium salts are prepared by adding cold solution of sodium nitrite, that is NaNO2, to aryl amine solution in dilute acid. And when we say cold solution, it is the 0 to 5 degrees centigrade temperature that has to be maintained. And then this process where we get these diazonium salts is called as the diazotization. The diazonium salts are always prepared fresh and used immediately because otherwise they will be unstable even at room temperature. If we look at the details, what is happening when we are taking NaNO2 and mixing it with acid, NaNO2 and HCl are in situ generating the unstable nitrous acid, as you can see in this equation. The nitrous acid so formed in situ further reacts with aryl amines to form the diazonium ion, as you can see in this particular equation. Let us now try to understand the mechanism of diazotization. The first step consists of formation of NO plus, that is nitrosonium ion, and dinitrogen trioxide. So, as you can see in this equation shown here, there will be protonation happening on HNO2, and because of this there is the formation of water and NO plus, that is nitrosonium ion. And this nitrosonium ion you can see here is resonance stabilized by these two structures. And also two molecules of HNO2 in a slow process, they will interact and form this dinitrogen trioxide along with water. The step 2 consists of either the attack of NO plus or the N2O3 on the amine, and as you can see here that when you have the aromatic amine, it will react with N2O3, and this is how you will have the formation of this next species, which is Ar with NH2 plus joined to NO. So, this nitrosation has happened here. And the step 3 is the loss of proton. From this species the proton is lost, and as a result you have the formation of ArNHNO, that is N nitrosation has happened here. The step 4 is the tautomerization, and as you can see in this equation, the hydrogen shifts to oxygen, and as a result what you get is Arn double bond N with OH. The step 5 consists of loss of water and formation of diazonium ion, and you can notice that here in the presence of acidic medium, there will be removal of this OH along with H coming from proton as water, and there will be formation of positive charge at this particular nitrogen, that is you get ArN2 plus, and this is what is the diazonium ion. Notice that here the positive charge is on the nitrogen joined to the aromatic or the phenyl ring and not on the terminal nitrogen. So, this terminal nitrogen you can see is not having the plus charge, it is the middle one because of these. Let us try to look at the stability of these diazonium ions. The aromatic diazonium salts are relatively more stable than aliphatic diazonium salts, as the electron rich benzene ring stabilizes the NN group which is joined to this particular phenyl ring. If the temperature rises above 5 degrees centigrade, the benzene diazonium chloride decomposes to form phenol and nitrogen gas is also given off as the byproduct. The aromatic groups present stabilizes the diazonium ion through electron donation via delocalization in comparison to aliphatic groups, as you can see in this equation. But note that this stabilization is happening only at 5 degrees or below those conditions and not at room temperature. Now, after this let us move to coupling reaction, that is how these benzene diazonium chlorides or these benzene diazonium salts can be further reacted with aromatic compounds and coupling can be done. So, if the benzene diazonium chloride is reacted with another compound containing a benzene ring, mostly as activated benzene which is joined to electron donating group, which is called as a coupling agent, for example phenol or aromatic amines, then it results in the formation of an azo compound, and these azo compounds are brilliantly colored. The diazonium salt acts as an electrophile in this coupling reaction. Many of the products of coupling reactions, as I told you, are very important dyes. A colored precipitate of azo compound is formed immediately on reaction with diazonium salt with amines or phenols, and this reaction is used as a test also for the aromatic amines as well as the phenols by taking the usual combinations. Let us consider some of the examples of coupling reactions. First of them is, as you can see here shown, that benzene diazonium salt and alkaline phenol will give rise to a yellow orange azo compound, which is this phenyl joined to NN double bond joined to another phenyl and then OH at the para position. Another example consists of that benzene diazonium salt reacts with alkaline naphthalene to all and it gives a red colored azo compound. So, this you can see is the structure here. You have the phenyl joined to NN double bond, which is the azo group here, and further joined at this second position and further joined to this naphthol, and you can see here this particular diazonium as electrophile has attacked to the position which is ortho to OH. Another example is the benzene diazonium salt with phenylamine, and it gives a yellow azo compound, as you can see in this structure. Now, let us move to understand the mechanism of this coupling reaction, which is giving rise to these dyes which are yellow to orange to red color. The mechanism involves an initial attack of coupling agent, that is phenols or anilines, on an electrophilic diazonium ion followed by a loss of proton. The product is normally a trans diazo compound rather than cis, and you can see here that this diazonium is attacking at the para position because of less steric hindrance, and the para position is being made electron rich by the electron donating effect of OH, and then once it attacks here it will be followed by deprotonation and the azo compound so formed. Notice that it is the trans in terms of the geometry around the NN double bond. Let us look at some of the uses of diazo compounds. Diazo compounds are very commonly used as pH indicators and dyes. First of all, Let us have the details of the pH indicators. The methyl yellow, methyl orange, methyl red, Congo red, alizarin yellow are some typical azo compounds which are used as pH indicators. Out of these, if you look at methyl orange is used as an acid base indicator in titrations. In solutions that are more basic than pH 4.4, methyl orange exists almost entirely as the yellow negative ion. In solutions that are more acidic than pH 3.2, it is protonated to form a red dipolar ion, as you can see in the structure. So, thus methyl orange can be used as an indicator for titrations that have their endpoints in the pH range of 3.2 to 4.4. In higher concentrations in basic solution, methyl orange appears as orange colored. If you look at the preparation of methyl orange can be prepared by the reaction of diazonium salt of sulfanylic acid and NN dimethyl aniline. Here again you can see that the mechanism will consist of first the formation of nitrosonium ion, and in order to obtain the nitrosonium ion, sodium nitrite has to be treated with HCl, as you are already aware. So, you can see in this equation the sodium nitrite, when reacts with HCl, there will be formation of HNO2, and HNO2 will further dissociate into NO+. Then the preparation of diazonium salt or sulfanylic acid. Sulfanylic acid is insoluble in acid solution. The first step is to dissolve sulfanylic acid in basic solution such as sodium carbonate, as you can see here, and in this basic medium the free aniline is generated because this carbonate will take out this proton. The next step is the attack of nitrosonium ion on the sodium salt of sulfanylic acid, as you can see here, and followed by there will be protonation. You can see here that this proton is given through this oxygen will be taking this proton, and next will be the tautomerization followed by the loss of water molecule and giving rise to this diazotized sulfanylic acid, that is the diazonium salt of sulfanylic acid is formed. After this, the next is the addition to NN dimethyl aniline. The finely divided diazonium salt is now allowed to react immediately with dimethyl aniline in the solution in which it was precipitated. The first product obtained from the coupling is the bright red acid form of methyl orange called as helianthine, and in basic medium helianthine is further converted to the orange sodium salt, which is commonly called as methyl orange. So, you can see here with the help of these equations that how the diazotized sulfanylic acid is attacked by the para position of NN dimethyl aniline, which is being made electron rich by the electron donating nature of this NN dimethyl group, and furthermore after the attack this proton will be lost here and there will be formation of this methyl orange. So, let us now go into some more details of azo dyes. Azo dyes are the compounds that contain two aromatic fragments connected by NN double bond. Azo compounds are stable, so the dyes do not fade. So, notice that the diazonium salts were unstable, but once you have formed the azo dyes, these are highly stable and they can be heated. Using different diazonium salts and coupling agents, one can make different colors. The colors of azo dyes include different shades of yellow, red, orange, brown and blues. The dyes are used to give colors to substances, especially fabrics, and you must have noticed when you have gone to some local market that some dye is being done, and you can see that these dyes are boiled with water and then the clothes are dipped into that and then furthermore washed with cold water and finally dried, and the color is transferred on these fabrics. So, colored substances absorb. So, if we try to see how the color is imparted, actually the colored substances absorb radiation in the visible region of the spectrum. The energy absorbed causes changes in electronic energy and electrons are promoted from a ground state to an excited state. The electrons excited in this case are the outer bonding electrons or the lone pairs. If you look at chromophores, chromophores are the functional group that absorb light, give color to these dyes, and the most common chromophore are various like azo, nitro, carbonyl groups. And what we are talking about in azo dyes, the chromophore is the azo, that is NN double bond joined to the conjugated phenyl rings. Oxochromes on the other hand are the functional group that increase the intensity of this basic color which is imparted by the chromophores, and they are also important parts of the dyes. So, if you take the azo dyes, the basic NN diazo functional group joined to phenyls is the basic unit or the minimum requirement you can say for color, and as you keep on putting more groups on either this or this phenyl ring, then the colors keeps on getting enhanced, and these are the oxochromes. So, the most common oxochromes are hydroxyl, amino, sulfonate and carboxylate groups, and varying these you can get different color of the basic dye unit. So, dear students, let us now summarize what we have learnt in this module. We have studied about two named reactions, that is we have studied about the Gattermann-Koch reaction and Vilsmeir-Haack reaction, both of which are very good for formylation. The reaction of an aromatic substrate with carbon monoxide and HCl in the presence of a Lewis acid catalyst to form an aromatic aldehyde, that is introduction of CHO group, is known as the Gattermann-Koch reaction. On the other hand, the reaction of electron rich aromatic compounds with DMF and POCl3 to yield an aromatic aldehyde is called as the Vilsmeir-Haack reaction, and POCl3 here reacts with tertiary amides to give the adduct which is known as Vilsmeir complexes. And then we have studied about the diazo compounds, what are diazonium salts, and then how the azo coupling or diazotization is done to get dyes. Compounds containing NN double bond group are known as diazo compounds. Aromatic diazonium salts are normally prepared from aryl amine, NaNO2 and HCl, and you have to keep in mind that for successful diazotization you must keep the temperature below 5 degrees centigrade, and the solution should be acidic, and the solution should have slight excess of nitrous acid. The diazonium salt need not be isolated and the reaction can be carried out in the same solution. The reaction of diazonium salt with aromatic ring is known as coupling reaction, and the overall reaction is a case of aromatic electrophilic substitution. And the aromatic azo compounds which are obtained by the coupling of diazonium salt with other electron rich aromatic compounds, they are called as azo dyes, and they have immense value in research and industry.